Hello and welcome. At this time, we are going to present our research about comparative analysis of deep learning model for classifying natural disaster image. Let's move to introduction. Samuel. Okay, nowadays we know that social media is critical platform for information sharing, especially when natural disaster is happening. Now imagine if this disaster news is include misinformation and noisy data, it can affect on individuals and severe impact on developing countries' agricultural growth and GDP. Our research is about uh, develop reliable image classification model for classification natural disaster detection from imagery social media. Okay, specifically, our model trained with cyclones, wildfires, floods, and earthquakes image. Of course, we have a challenge, but this research challenge that we face is about data quality and optimizing model. Talking about the data quality, the data has inconsistent image resolution because obtained from social media and news footage. For optimizing model training, we have to balancing the trade-off between model accuracy, training time, and the complexity. And we have to move to that works. Okay. Next, sorry. We obtain information about deep learning models that mostly used for this task is EfficientNet, CNN, VGG, GAN, and Decision Tree. Okay, next. From that related works, we can get several important key, which can be our baseline for our research. Okay, it's enough for me.
And for the methodology, first we loading the data set, we resize the image, we transform the data, we split data, we do the data augmentation, and then we do model deployment plus fine tuning, and we evaluate the result. For loading the dataset was provided by Gautam Kumar through his LinkedIn profile through PyImageSearch website. It contains over 4,400 human annotated images, categorizing for disaster types, cyclones, earthquake, floods, and wildfires. For an resized image, in order to create consistency and uniformity, every image is downsized to 224 by 224 pixels for all models, using 3 color channels to guarantee compatibility across the spectrum. Additionally, a crucial conversion takes place to handle black and white photographs, methodically transforming them into a RGB spectrum to guarantee true feature representation. And the data transformation, images converted to NumPy arrays for manipulation and analysis, crucial for subsequent modeling and processing. And for label encoding, scikit-learn's label binarizer encrypts category labels in binary format. And for data splitting, we split the data to 75% training set and 25% test set. And from 10% of the training set, we use it to be used as validation set. And for data augmentation, we apply various augmentation techniques such as rotation and zoom, shifting, shearing, and horizontal or vertical flipping. And the model selection that we use VGG16, EfficientNet B0, ResNet 50, and VGG 19. And for the selection rationale, with the comparative analysis among deep learning models for image-based natural disasters detection. When we compare VGG16 and VGG19 depths within the VGG architecture, and we also include ResNet 50 and EfficientNet B0 for diverse architectural approaches. And for supporting fair and consistent assessment, we ensure consistency across dataset usage, training parameters, architecture, and protocols. We also enhance validity and fairness in comparative analysis, fostering unbiased evaluation of model performance. For consistent dataset configuration, we employ identical training, validation, and test set across all models for unbiased evaluation. Standardized training parameters, we use the same learning rate and the fixed base size, which is 32 for each model. And transform learning approaches, we utilize frozen-based architecture layers with pre-trained weights for transfer learning benefits. And uniform training schedule consistent 48 epochs for all models, ensuring uniform learning iteration and convergence. And we also apply cyclic LR callback initialization for dynamic learning rate adjustments. And we also use validation data consistently throughout model iteration for fair evaluation. And for evaluation, we use classification report to show the precision, the recall, F1 score, and overall accuracy for each disasters.
For chapter 4, results and discussion, we have the results table in right over here. For the insight, first we have the performance insight that cyclones can easily classified with high metrics across all models, and flaws pose challenges, showing lower precision and recall. For our top performance, we have FreshNet 50 and EfficientNet B0 that achieve 96% of accuracy. For model efficiency consideration, we have VGG16 and VGG19 with slightly lower accuracy but shorter training times. And for our model training performance can be shown in this table, with the second table showing the relationship and interpretation. And for the training performance insight, FlashNet 50 and EfficientNet B0 consistently displaying higher final epoch accuracies. And for consideration for larger dataset, we have VGG16 and VGG19 with shorter training times that could demonstrate notable speed advantages with larger dataset. And VGG19 appeared approximately 1.12% faster than VGG16, 5.29 faster than ResNet 50, and 4.98% faster than AVCNet B0 in training time. And for scaling advantage, we have scaling up dataset size may amplify the speed advantage, potentially showcasing a more pronounced increase in speed for VGG19 compared to other models. And we go to the individual model training performance. For each model, we have the graph for training and validation accuracy graph in here, and also the training and validation loss. For the insight, we first have VGG16. Based on the results, it indicates potential overfitting and lacking convergence. For EfficientNet B0, it signifies convergence and stability based on the results. And for ResNet 50, we have the similar results as EfficientNet B0, showcasing high convergence. And for VGD19, indicating convergence with room for improvement. And for the final chapter, conclusion, we have several conclusions. For model performance, we have ResNet 50 and EfficientNet B0 consistently outperform VGG16 and VGG19 in accuracy across diverse disaster categories. But for the trade-off, we have VGG16 and VGG19 balancing the computational economy for shorter training times. For the convergence insight, we have ResNet 50 demonstrating a high convergence and stability. EfficientNet B0 exhibits convergence with slight accuracy and gap variations, and VGG 16 and 19 showing more gaps, suggesting potential overfitting and less convergence. However, for optimization opportunities, VGG 19 exhibiting better convergence than VGG 16 that can be optimized for improved performance. For larger datasets consideration, for VGG19 has a significant training time advantage, which is applicable for rapid model development and deployment. For the final conclusion, we conclude that choosing the best model requires balancing accuracy, convergence, and computational efficiency. The research provides valuable insight into model strengths and weaknesses, aiding informed decision-making in disaster management. An effective model choice enhances disaster response and management strategies, contributing to a more resilient communities. Thank you for listening to our paper presentation. Thank you.